Okay, after this very theoretical talk, I would like this opportunity here to talk about a little bit more technical, in particular about some work that has been conducted in the lab of Nonreciprocal before he moved to Berlin, which was a work on non-reciprocal quantum devices using our cavity quantum electrodynamics experiment. And yeah, in order to give you some motivation why you would need such non-reciprocal devices, let's also start with some network or quantum networks where you start off with one processor, quantum processor A, and you would like to connect it to several other processors via different links, and you want to send, for example, establish entanglement between A and B, and for that you would like to send a signal from A to B, and you have to make sure now that the signal actually arrives at B and is not reflected or accidentally going to C. And furthermore, if you then also want to send a signal from B to C, you also need some devices that make sure that your signal actually goes where you want it to go. And for this, you, on the one hand side, need some kind of switches, and more importantly, you need some kind of non-reciprocal components. First of all, for example, isolators, which allow, for example, only unidirectional transmission of a signal, or circulators, which enable you to send the signal from one port to the next one, and so on. Good, and for example, in microwave electronics, such devices are available off the shelf. But if you would like to have a network which spans over larger distances, you would probably prefer optical photons. And these non-reciprocal components are available for bulk free space optics, which then look something like this. But if you would like to integrate them, if you want to reduce the footprint and still make it work at single photons and still only have low losses, this is still an outstanding challenge. And in order to give you an idea why this is the case, let's have a quick look how such a free space optical circulator, isolator or circulator works. So all of these devices, which you might have seen in some laser lab because they are placed behind your laser diode in order to prevent some signals to come back, work in the following way. So if you send light from one direction, they will transmit, but if you send it in reverse direction, the light will be blocked. And this is, all these free space isolators are based on the Faraday rotation, where you take some magneto-optical crystal, bias it with a strong magnetic field, and if you now send linear polarized light through this magneto-optical crystal, the polarization will rotate. And if you now choose the material, the magnetic field, and the length of your crystal such that after passing through the crystal once, you rotate by 45 degrees, then every light that comes in the opposite direction will rotate in the same direction, and thus, if you put a polarization filter here, that only where only a linear polarized light that is polarized like the initial beam will pass, it should be blocked at this point. And if you now replace the polarizer here and at the end by polarizing beam splitter cubes, you can actually directly create an optical circulator which works like this. So if you send light in here, it will exit here. If you light enters here, it will be sent here, and so on. So this is then directly an optical circulator. You might wonder now why this is so hard to integrate, and there you can think of just why don't you put your Faraday rotator, this magneto-optical material, as your waveguide, and this has several problems. First of all, your waveguides are highly birefringent, so you cannot really rotate your polarization. You need some integrated magnetic fields which are sufficiently large, and if you make now your crystal smaller and smaller, you will introduce more and more losses to your waveguide, which is also not beneficial. So people try to think of new concepts. For example, they try to use the non-reciprocal phase shift by placing such a magneto-optical crystal on top of a ring resonator. And if you now bias it appropriately, then depending on whether the light rotates in one direction or the other direction in this ring resonator, it will have a different resonance frequency. So if you now sit on one resonance frequency, it will be blocked from one side while it will be transmitted from the other side. And in our experiment, we now drove this approach to the fundamental limit, where we replaced this magneto-optical crystal by a single atom, which is strongly coupled to not a ring resonator, but an ultra-high Q whispering gallery mode resonator. Good. After this short motivation, the talk is structured as follows. So we'll introduce you to our workhorse, which is the bottle microresonator and its special properties. And then I will continue with how in these resonators chiral light-matter interaction comes about. And then I will also tell you how we can use this chiral light-matter interaction to actually realize an isolator and circulator. Good. So I was talking about strong light-matter interaction already. So what people usually do is they want to have light which is guided in some kind of fiber or waveguide to interact strongly with an atom. But usually this interaction is very weak. So we take now the detour to first couple the light into a so-called whispering gallery mode resonator, where now the light circulates around the circumference many thousand times, forming a mode. And we can now couple this mode then to an atom by placing this atom, for example, in the evanescent field of these resonator modes. And we usually speak of strong coupling if now this coherent energy exchange rate between the atom and the resonator mode is much larger than all the decay channels. And these decay channels now include the resonator decay rate, comprised of the intrinsic losses and the losses to the waveguide, and the atomic decay rate. And this parameter here is in our community often referred to as cooperativity and should be much larger than 1. And this is also also proportional to the quality factor of our resonator divided by the volume. So you want to have a resonator where the light stays in very long, and the light should be compressed on a smallest possible volume. And in our case, we now realize such a system by using our bottle microresonator, which is fabricated from a commercial optical fiber, first pulled down to a diameter of roughly 40 microns, and then micro-tapered again to give this bottle-like shape. And these resonators can now be interfaced via optical nanofibers, where you can have almost lossless coupling by overlapping the evanescent field of the fiber with the resonator mode. Good, and in typical experiments, where we place single rubidium atoms in these evanescent fields, we get these parameters which put us in a so-called strong coupling regime. However, this strong coupling regime is not all we need for realizing these non-reciprocal devices. And for knowing how these now work, or what we actually need, we have to take a closer look at the polarization properties of these resonator modes. And for this, we can now zoom in and assume that our resonator can be approximated by a planar interface where we have an impinging plane wave. And we now assume, for this case now, a polarization of the incoming beam to lie in the plane of the screen. And for this case, we have here the evanescent field for if we have total internal reflection, where we have two polarization components. We have an effective propagation in z direction and the exponential decay of the evanescent field in x direction. And if we now want to know how large this counterintuitive longitudinal component, which oscillates in direction of propagation, is, we can consult Gauss Law, which tells us that these two components relate by this ratio here, where you have, first of all, the decay constant beta of this field, and the wave number. So this tells you whenever you have a very strong gradient in direction of a polarization component, you get a strong longitudinal field. In addition, what you also see here, that these two field components are 90 degrees out of phase. That means you get elliptical polarization. And elliptical polarization where the ellipticity is in the plane spanned by the propagation axis and the second axis. And if we now put in some numbers and consider Kreising incidence of the incoming beam and the interface between silica and air, we get an overlap between this polarization and perfect circular polarization of 97%. So we can assume that this is almost perfectly circular polarization. In addition, if you now have some circular polarization or elliptical polarization, you can associate some kind of photon spin with it, which is in this case transverse because it's pointing out of the plane of the screen and transverse to the propagation direction. The nice or most important feature of these transverse spin components of light fields is that they are inherently linked to the propagation direction. What does this mean? If you now reverse the propagation direction of your evanescent field, the photon spin changes. What does this mean? It means that now the circular polarization, the electric field rotates in the opposite direction. So if you had sigma plus polarized light before, you will have now the orthogonal circular polarized light sigma minus if you just reverse the propagation direction. And this is called spin momentum locking of light. Good. Now as a next step, we will see how now these special polarization properties will influence the coupling between light and matter. So let's again have our resonator here, and we have our coupling fiber interfacing this resonator, and we can now send in light from one direction, thereby populating one of the two counter-propagating modes of our resonator, and the evanescent field will now have, for example, sigma plus polarized light. If you now probe from the opposite direction, thereby populating the counter-propagating mode, we get sigma minus polarized light. And if we now couple an atom to it, we now have to consider not just the two-level system, but the full complex level structure of this atom, including all the full Zeeman manifold, because different polarization now will drive different transitions of our atom. And if we now consider the case where the atom is prepared in the outermost Zeeman state, and we probe our system from one side, this sigma plus polarization of the evanescent field will exclusively drive this transition here. And once the atom is excited and wishes to decay, since this is a closed cycling transition, it can only decay back into the same state that it came from, meaning that it has to emit again a sigma plus polarized photon, which can only be emitted into the same mode that it was excited to from. And this can then only exit in forward direction from our resonator. So this gives some kind of direction channeling of the atom into the same mode that it was excited from. And in our particular case, this gives us the ideal situation where we have, even though we consider a multi-level atom, only two levels involved, and these two levels exclusively coupled to a single resonator mode, even though we have these two degenerate counter-propagating modes available. And if we now look at the spectrum of such a coupled system and compare it to the empty resonator, which is just a Lorentzian, we obtain this vacuum Rabi splitting where now this 2-dip spectrum gives the splitting gives 2 times the coupling strength of this particular transition. And just to mention it, for a usual ring resonator, you would expect actually not a 2-dip, but a 3-dip spectrum, because you always have part of the light in the mode which does not couple to the atom at this very position, meaning that only half of the light would couple to the atom. But due to this directional channeling, we can actually get all the light coupling to the atom. Good, and now you can ask the question, what happens now if we send in light from the opposite direction, thereby having a different polarization of the evanescent field? This should couple now these two states. And if you look at the transition strength, you can just compile the Clebsch-Gordon coefficients, and you see that one of those is much weaker than the competing transition, meaning that you have now a direction-dependent light-matter coupling by just interfacing a polarization-dependent scatterer with spin momentum-locked light. And if you now also measure the transmission spectrum, you observe a spectrum which resembles that of an empty resonator. Good, so these are more or less the key features of chiral light-matter interaction. First of all, you get this ideal situation of two levels coupling to a single mode, and you get also this direction-dependent light-matter coupling. So how can we now build an isolator and a circulator out of this? So if we now, again, have the same spectrum as before, we probe from one direction where we strongly couple to the atom, and we look on resonance. You could argue that now the atom on resonance shifts the resonance frequency of the resonator, thereby the light cannot enter the resonator and it will just stay in the coupling fiber and will be transmitted. This gives this high transmission on resonance. But if you now change the probing direction, the coupling strength is much weaker, so the light is still resonant with the resonator, so it can enter and be dissipated in the resonator. If we now set the so-called critical coupling condition correctly, this point here will really go down to 0 because you balance the loss rate of your resonator with the coupling rate between the resonator and the waveguide. And this already gives you the functionality of an optical diode where you have high transmission in one direction and zero transmission in the other direction. And if we calculate the isolation of this device, we get 13 dB and a forward transmission of 70%, which is already was unprecedented for integrated devices. If you now want at some point to make use of your quantumness of the atom, you somehow have to get rid of this dissipated channel because one direction always the photon is lost, which kills all your quantumness. So one way to do this is to add a second coupling fiber to the system. So if you now probe from one direction, the atom again prevents the light from entering into the resonator, and it will be transmitted. But if you probe the opposite direction, it doesn't see the atom, it will circulate in the resonator and eventually exit at port 3. And if you send it now light from port 3, it will again couple strongly to the atom and thereby will be transmitted. And here it doesn't see the atom, enter the resonator and exit at port 1. So this gives you already the functionality of a 4-port optical circulator. Good. In our experiment, however, we have to find a trade-off between having a strong effect of the atom, which introduces this non-reciprocity, and having an efficient coupling between the two fibers via the resonator. And in order to find the optimal working point, we can now adjust the position of one fiber while leaving the other fiber always at critical coupling, and send in light from all directions and measure the transmission or the signal at each output port. And you now have to believe me that this is now the obvious optimal point. And a more convenient way to plot this now is to use the so-called transmission matrix, where you have the input on one axis and the output on the other axis, and you just give the value of the transmission between these 2 points. And for the ideal perfect circulator, you see that all the light incident on port 1 should be sent to 2, 2 to 3, 3 to 4, and 4 to 1. And you see that this is non-reciprocal by the fact that this is not symmetrical with respect to the diagonal. And if we now compare this to our measurements, we get very good qualitative agreement. And if we split the circulator into 4 independent isolators, we get isolations between 10 and 5 dB and an average survival probability of 70%. And this was somehow the first demonstration of a low-loss integrated circulator, which should also be compatible with quantum information processing. But that's not all I would like to mention here, because since the atom can be prepared also in the opposite Simon ground state, by which we inverse the role of sigma plus and sigma minus polarization, we can invert the operation direction of a circulator, meaning that this here just flips by its diagonal. So now the light is sent from 1 to port 4, from 2 to 1, and so on. So this gives us also the possibility to control the operation direction of our circulator by a quantum state and make it thereby programmable. Furthermore, we can also create some kind of superposition between these two operation directions and create some quantum circulator, which can play an active part in some quantum information processing. Good. having talked about quantum features of our resonator, I would also like to mention another quantum feature, which comes about if we look at the photon statistics, because our atom, which introduces this non-reciprocity, is a nonlinear absorber, which means that it acts differently depending on the number of photons that it encounters. Which means if we now send a single photon in, everything that I said is true, so the atom prevents the photon from entering the resonator and it should be transmitted. But if we now have 2 photons instead of 1, the interaction strength, the effective interaction strength between the photon and the atom changes, because already the first photon saturates the atom, so the 2 photons can now enter the resonator and will leave at port 4. In order to make this visible in our experiment, we can put some Henbury Brown twists set up at each output port and measure the correlation functions. And at the port where we expect only a single photons to exit, we see a clear anti-bunching in the transmission. And for the port where we expect the pairs of photons to exit, we actually get a strong bunching at 0 time delay of these coincidences. And you might wonder what this can be used for. So this is now a so-called Photon Sorter, which can also be used, for example, for error-proof Bell state analyzers. Good. If we now have our quantum functionalities, our classical functionalities, you could think of putting more of these circulators together to create multi-port devices. Or you can create some networks out of it where if all the atoms are prepared in the same state, light will circulate always between 4 of these circulators. You can reverse the propagation directions of these photons in the network. You can also create some kind of channels where light can be transmitted. Or if you make use of the quantumness, you can also make even more crazy schemes where this might be used as a new resource for quantum computation and quantum simulation. Good, I have no idea. I think I've been very fast. So let me quickly summarize what I've told you. So I introduced it to our workhorse, which is the bottle microresonator. I've introduced it to its special properties, including spin momentum of light, which I probably haven't mentioned, but it's not a special feature of our resonator, but you can encounter it for every for example, for tightly focused Gaussian beams as well as nanofibers, wherever you have a strong gradient in direction of a polarization component. And if you now have this spin momentum locking and couple it to a polarization-depending scatterer, you get this chiral light-matter interaction where you get direction channeling and direction-depending coupling strengths. And this can, I hope, and I've shown you how you can use this to realize these non-reciprocal devices, where we have shown non-reciprocal transmission at the single photon level. And we also demonstrated that we can change the operation direction, and we also have shown some nonlinear behavior, which can be used for photon sorting. Good, with this I would like to thank you for your attention and show you the people that were involved in these experiments. So, thank you.
Okay, thank you very much for the presentation. Questions? You were first.
Hey, thanks for the talk. It was very interesting. So I just wanted to ask, on slide 28, you showed the kind of weighted matrices, and you had numbers around 0.5 to 0.7. I was just interested in what are the limiting factors there that stop you getting up closer?
At the moment, the main limiting factor is the quality factor of our resonator. So in principle, in order to make somehow in order to make efficient coupling between those two fibers, you ideally want to couple both of these fibers critically, meaning that they balance with the losses of the resonator itself, so the coupling rates. And this can only be reached when somehow the intrinsic losses are 0. So whenever this is non-zero, this will make your resonator bad, your circulator bad. So this is, and if you, and the second thing is then of course the non-perfect polarization, So then this 97% gives you then another factor which deteriorates your signal here.
Okay, cool. Thank you.
Thank you. I think this is now very polarization dependent, isn't it? I mean,
sorry.
It only works for one polarization. This is this correct?
For input polarization.
Exactly. Yeah.
Yes. So of course. So I think I did not really mention it. So you have two orthogonal polarizations of your resonator, eigenmodes. So these TM modes and TE modes, but usually they are anyways not resonant for the same frequency. So this is a very, you could say this is anyways very narrow band because you have to hit this resonance, and for the same frequency, the opposite polarization will anyways not couple to the resonator mode. So of course you have to have the right polarization as an input in order to, well, I think this will take some time. I think it doesn't help.
But this is only the longitudinal component of the polarization that couples to the atom, right?
Exactly. So first of all, for these schemes, you need these TM modes. These TM modes are the only modes that show this spin momentum locking. Otherwise, you would. So maybe I should go back. So what you require here is, in this scheme where you have the planar polarization, you have two possibilities. One where the light is initially polarized in the plane of the screen, and the other one where it points outwards. And this also corresponds to the two possible eigenpolarizations of your resonator mode, TE and TM modes. And you require now the polarization which is in the plane of the screen, because you need the polarization pointing in direction of the strong gradient, which is now given by the exponential decay in x direction. If you now have the opposite eigenpolarization, your field would oscillate in this direction, and you would not get an additional longitudinal component. So you would not get any elliptical polarization, therefore you get no spin momentum locking, and therefore the whole non-reciprocity doesn't work. So you have then no spin momentum locking, and it doesn't matter how you couple your atom to it, it will always see the same light field for these resonator modes.
Well, in principle, it would be possible to build, I don't know, two of these systems and then split any arbitrary polarization up and
sure,
combine it afterwards?
You can just put two systems there. You put a polarizing beam splitter and then rotate it that both of them couple to a TM mode. Would work, yes, but it's not very convenient. In particular, since you also have to make sure that your resonator has then the correct resonance condition and stuff like this. It would work, but not well.
Okay.
Mine is a simple question about single photons versus weak pulses.
Yes.
Are you likely? It's always one of the things that I know these experiments quite well. So, I mean, do you expect any differences when you go to real single photons?
Yes,
Right.
I would say yes. So you're speaking of now the experiment where he saw this nonlinearity, of course. So we do not have a single photon source or a two photon source available. So what we do is we just use weak coherent pulses. And to my understanding, all we say somehow works well for weak coherent pulses, because at the end, if you really make a pulse with two photons, you come into some bandwidth problem. So you have to make a pulse, which you have to make shorter to make sure that you have your photons. Then this has to be in the bandwidth of your system, which is given somehow by the whatever Purcell enhanced line width of your atom. And somehow these two photons in this pulse have to be within the line width of your system. So you get into, so I think there's this Shapiro argument that somehow you...
But yeah. What happens if you have, let's say, not a weak coherent pulse and put it on these things? You get then...
Oh, sorry, I don't get it.
If you put not a weak coherent pulse, one that has really like a coherent pulse, but not weak, and put it on your device.
So everything I told you only works in principle for single photons. So all these vacuum Rabi splitting works for single photons. So if you start to increase the power, then you get these nonlinear effects that your atom just doesn't act the same for a single photons or 10 photons.
Would I then just get out on the, let's say, single photon channel that you showed there, just single photons out, and all the rest goes of the state goes around?
Yeah, you can use this as something like a single photon subtractor. So Baraktaryan did exactly this. So he sent a pulse of n photons onto more or less exactly the same system, and he extracted only single photons on one of these output ports. So this is actually possible, yeah.